Okay, then let me give the outline or the framework basically that Murto and Nese study in their working paper. So their question, as I already alluded to, is about a choice between two different investments. So on the one hand, there is this firm that has the option to build a gas-fired electricity generation plant on a plot of land. But there's an alternative to that. It can, instead of building a gas-fired plant, it can also build a biomass plant. But of course, it can only build one because it only has one plot of land. So the question is, which one will be the desired one? And you can imagine that that's going to depend on the values, and the present values in particular, the worth of doing either of these, choosing either of these two alternatives. So the interesting thing here is, of course, that we are going to introduce some form of uncertainty here, and the uncertainty that we're going to have a look at in this paper is that the gas price is going to be uncertain. So in particular, the gas price follows geometric Brownian motion. So why is this important? Well, of course, gas is an input for this gas-fired plant, right? So if gas is more expensive, it's going to be less attractive to build a gas-fired plant, and you might imagine that if gas is really expensive, then you will really like to make the investment in the biomass plant instead, whereas if gas is really very cheap, then you'll be more inclined to invest into this gas-fired plant. So gas here, the price here is actually a cost, right? It's a cost in particular to one of these two alternatives, and actually it's not a cost to this, not a direct cost at least to this biomass plant, of course. So the other parameters, just for the sake of clarity here, are fixed. So in reality, of course, there would also be uncertain, but just for this paper, in this paper, the authors are going to take those fixed because it's already enough of a handful to actually work out the implications of this fluctuating gas price. So in particular, the price of the electricity that you're going to produce, which is the output of both firms, is going to be fixed, the electricity price. The price for biomass, which is the input for this biomass plant, that's going to be fixed. The costs of investments in either of these plants are going to be fixed, and any subsidies that might be there are also going to be fixed. So the only stochastic part here, the only fluctuating part, is this gas price P. So as I just basically tried to point out already, if this gas price is really high, you're going to invest into the biomass plant, because then investing in a gas-fired plant is going to be a really costly affair, so you won't, the price of electricity will not be high enough to earn back this price, this cost of gas essentially. So if the gas price is low, on the other hand, it's going to be really attractive to invest into the gas-fired plant, because then you make a nice margin on selling the electricity over the buying the input cost of gas. And now the interesting thing, of course, is if the gas price is in between two thresholds, the green one and the red one in this case, then it's going to pay to wait. So it might go either way. So you would like to wait until either this blue line, the gas price, the price P, is going far enough up to cross the green dashed line, in which case you will invest into in this biomass plant, or perhaps the gas price goes down and it might cross the red dashed line, and that when it crosses that threshold, the investment should be made into the gas-fired plant instead. And of course, the whole analysis is should have as our goal to figure out what are those two thresholds. So where is this threshold? How high is this green threshold for investing in the green alternative, in the biomass alternative, versus how low should gas prices go when we would like to sort of make the investment in the gas-fired plant. So now, of course, if you invest in one technology, that means, of course, you incur the investment cost in that one technology, but it means more because you're also giving up the option to wait a bit longer. So that's like we already saw before. When you make an investment, you give up an option to wait longer before making the investment at an even later stage. But in this case, this option also, there's also basically an option of investing in the other technology instead. So if you're still in between, then actually price might reverse and might actually go the other way. And then you might actually prefer exposed to have invested in the other technology instead. So you also have to take into account the value of that option to not invest in one technology, but instead invest into the other technology. So these thresholds here, they will reflect those costs, those opportunity costs of throwing away that option value. So both the option value of waiting longer and the option value of being able to invest instead in the alternative technology. Again, we want to figure out how high are these option values, because this will allow us to figure out where should these thresholds be. So that's what we set out to solve. So what are the parameters here? Well, first of all, we have this price of gas, which is stochastic, which follows some geometrical random motion process. So with the mu, the drift rate that we know, and the sigma, the volatility, measuring the level of uncertainty in this gas price. So that's the stochastic part, and the fixed part are the electricity prices I mentioned. We're going to fix that at a level which in the paper is called A, so let's just stick with that name, it's called A. We have an investment cost for the gas-fired plant, that's called I, so that once you decide to make the investment in the gas-fired plant, you're going to sink an investment cost equal to I. And then all the other parameters relating to the biomass plant, so with the investment cost in the biomass plant, and the value of the electricity produced from this biomass plant, perhaps some subsidies if those are included. We all summarize those into a single variable because all of that is fixed. I'm just going to summarize this in one parameter, which is called V of R for renewable. So that's the NPV, the total NPV of investing in this renewable plant. So it includes in particular the investment costs as well in this biomass plant. So those are the parameters that we have. So the mu and the sigma, of course, we have the interest rate as well. We have the electricity price A with the investment cost for investing in the gas-fired power plant, and we have the total present value, the net present value of investing in the renewable biomass plant. So what will the analysis now look like? Well, we have to figure out, of course, what we're going to do is first figure out what's actually the value of having a finished gas plant. So once we make this investment in the gas plant, we get a gas-fired plant. Well, what's that worth? Well, it's of course going to be close to what we did before. So it's going to be close to this growing perpetuity kind of value. But we're actually going to adapt this a little bit because we have to sort of recognize that in this case, what's your operational profits? What is that going to look like? Well, this flow of profits is, of course, the difference between the electricity price that we make, A, minus the price of gas that we incur in order to make this, to produce this electricity, which is P. So that P is going up and down. And it might, of course, be that this price P is going above and beyond the value of electricity. So what would you do in that case if the price of the input of the fuel is larger than the value of the output, the electricity? Well, in that case, you would rather shut down or at least suspend operations of your gas-fired plant. You switch it off, and you will only switch it on again when the gas price again falls below the price of electricity and when production becomes profitable again. So we are actually going to compute the value of such a plant, which you can switch off when it's not productive. So when the input for the fuel price is above the electricity price. So that's the first task, which involves a real option computation as well, actually, as we'll see. Then the second task, once we'll know that, we're going to look at the restricted problem where we ignore this biomass option. So we are just going to look at the investment problem where we are going to choose between either waiting or making the investment into this gas-fired plant, which will have this value V of G that we have computed in step 1. So that's just an intermediate step to see how that works. It's basically similar to what we did before, but now with a slightly more complicated, as a result of this shutdown option, a more complicated value of the power plant. And then finally we go to step 3, in which we include again this biomass option, and we're going to state essentially and then solve the full option. In which case we can write down the equations. We cannot explicitly solve those analytically, so we'll have to do with a numerical approximation, a numerical simulation basically of those equations. So that will be basically the tasks ahead of us for this paper. So it will be the solution method. So in each of these steps, basically we're going to work according to the methodology that we have been looking at so far. So first we are going to look at these different regimes. It might be a weighting regime, or a production regime, or an investment, in a PV, immediate investment regime. We identify those, and then we identify the solution for the value as a function of the price of gas P in each of these individual regimes. And these solutions, particularly in those weighting regimes, will look like a solution to Bellman equations. So we have to solve those Bellman equations again. And then we have to match up those different regimes at the boundaries. So these boundaries might either be at p equals 0, or in this case also at p equals infinity, as we'll see. Or rather, they might be at the thresholds at which we cross to a different regime, and they will have value matching and smooth pasting at these price thresholds. So that's what we need to solve. So with that as our program for today, basically, let's get on with that next video with this first part. What happens with the value of a power plant if you can actually temporarily switch it off when the costs of running it actually exceed the benefits of selling the electricity that you produce.